Syzygy, episode 59, Living with a Star. And welcome back for another edition of the Syzygy podcast. My name is Chris Stewart. Sitting opposite me at the table, as ever, Emily Brunsden. Hey, Emily.
Hello, hello.
You've just fed me an enormous donut filled with Nutella, and I'm thankful, but also feeling a little bit...
You just need to wait for the sugar to kick in. It'll be great.
I'm waiting for it, the sugar and the caffeine. But, I mean, this is a holdover from the pancake episode last time. Pancakes last time, donuts this time. I'm a little bit worried about what happens next. Anyway, let's carry on. Today, we're going to be talking about the sun, because the sun's been in the astronomical news a little bit lately. There was a launch of a new spacecraft, which was heading off sort of in the general direction of the sun to do some really interesting stuff. And then there was also some quite staggering, I mean, you had to have your head buried under a rock somewhere not to see it all over the headlines. Amazing images of the surface of the sun in detail like we've never had before. The origins of which, those images, those videos, are really quite extraordinary. So we're going to be having a bit of a chat about that today, Emily.
Yes, we are. And also about another, I mean, it would be reminiscent of us to talk about solar sort of missions without talking about the big solar orbiter that's going out round at the moment.
At the moment,
so
right
that's the
there.
Parker Solar Probe.
The closest thing we've ever had to the sun. Yeah,
yes,
we're going to be talking about that. Okay, so where do we dive into this one then? I mean, the sun is clearly... You don't dive into the sun. That's a bad idea, by the way.
Yeah, don't do that.
Yeah, don't look at the sun. Don't dive into it. The sun is clearly a very important thing for the solar system. It's in the name, right?
Yes.
So we should probably talk a little bit about the sun.
Yeah.
And what it is.
So with all of these missions and observations, we're going to be talking about what they're trying to learn, right? And a lot of what they're trying to learn is different parts of the outer sort of layers of the sun. So it's worth giving a quick recap of what actually are the outer layers of the sun and why they're quite interesting.
I mean, you might naively think that, the sun, it's quite big, it's quite near, of all the things, surely that's the one that we would know the most about because it's just there. You can just look at it. Don't look at the sun. That's a bad thing to do. But don't we know everything about the sun already?
No, not by
Really?
any stretch of the imagination.
But it's just there, Emily. I mean, you can almost touch it. Come on.
It's such a mysterious place. There's so much interesting physics and astrophysics going on that we just need to make more observations to be able to understand our full stellar environment.
And is that because it's far more big and interesting and complicated than we think? Or is it because it's actually really difficult to look at the sun and do interesting measurements? Why? Why have we not?
All of these things are true. Yeah, so it is difficult to observe the sun. I mean, we're going to be talking about one of the biggest ground-based telescope ever to look at the sun. And it's kind of small compared to the stuff that we use to look at, say, stars and galaxies.
Sure.
Right? And it's also because the sun is really complicated. And if you want to understand the detail of what the sun is, what it's doing as part of its kind of fusion life cycle, but even more importantly, what it's doing on the surface, you need to understand some really crazy hard physics. Mm-hmm. So we get into the realm very quickly of something called magnetohydrodynamics.
Hey, I think that's come up on the podcast before, and I think it's, if that's not the name of a prog rock band from the 70s, it ought to be. So how do we start? Talk to me about the sun.
Let's start with the surface that we kind of see, if you like, that you don't look at, but is...
But if you could, you would... Oh,
look,
can we just be very upfront on this and just have it as a given? We're not looking at the sun directly. There are very special ways to do this that professionals use.
Yes.
Yeah.
Okay, so the surface of the sun, if you like, that we look at is called the photosphere. Mm-hmm. And interestingly, this is actually the coldest part of the sun.
Cold in the sense of how cold?
So we're talking about 6,000 degrees.
Right, just a mere 6K, sure.
Yeah, but it's interesting to think that the bit we see, the bit that all the photons come from, is actually the coolest part of the entire sun.
Yeah, okay. Still very, very, very hot, but it's the coolest bit. And it's when you say it's where all the photons come from, I mean, the light in all of its wavelengths that comes to us, I mean, eventually it's got to leave the sun and head off into space and hit our eyeballs. So this is the last surface, like the last bit of the sun beyond which the photons just flow out of. Inside the sun, it's a lot more complicated.
Yeah, so there's photons being produced from the interior of the sun and they travel out to the surface. What we mean by where the photons come from is that it's not that the sun is opaque beyond this layer. So we don't see inside the sun directly.
Right. Okay.
Yeah. So the photospheres, so this is what we say when we say the radius of the sun and things like that. Now, the next layer out from that, the sun doesn't just stop
Right. It's not a hard line.
No. In fact, some of my favorite quotes from solar astronomers are things like, we actually just live inside the atmosphere of the sun.
Okay. Yeah.
Because it does. The sun has this kind of extended influence in the entire solar system. And the first part of that extended atmosphere is a bit we call the corona. And the corona you might have seen pictures of, particularly pictures of solar eclipses.
Yes. So when you do get the full solar eclipse, the world goes dark. And if you are very, very careful, then you can see the moon blotting out the sun in its entirety, except for this suddenly visible, amazing, blanket, ghost-like around the disk of the sun, and that's the corona. So what is that?
So this is the extended atmosphere from the surface of the photosphere. It extends a few million kilometers out from the surface of the sun, and I think the most exciting thing about the corona is that it's hot, really, really,
All right,
really
so
hot.
hang on, you said the coldest bit, okay, not necessarily cold, but the coldest bit is the very surface, the photosphere. And that's 6,000. So now you're talking hot. And so in the context of the sun, how hot is the corona?
So the corona is several million degrees.
Holy cow. Okay. Yeah, that's really hot.
That's really, really hot.
So what is it? Why is it so hot?
Well, that's actually a really good question.
And
we're not entirely sure the answer to that one.
Okay, so we've already started. We're only on item number 2 in our list of things at the surface of the sun. And we're only on item number 2, and we're already at the dunno. Yeah. not sure about that one.
Well, yeah.
There must be a guess.
We have some ideas. So what's happening is you've got plasma. So the sun's not, this burning fiery ball. That's plasma that's moving around. And plasma's charged particles. Charged particles do crazy things with magnetic fields. There's probably some kind of energy movement mechanism from the sun into the corona. And that could be to do with waves that are traveling out into the corona and dumping energy basically into that. That's all tied up in the magnetic fields that we have. These are also the same sort of waves, interestingly, that we study when we try to make fusion reactions happen here on Earth, Alvin waves and things like that. So that could be one sort of partial explanation or the whole explanation. Or it could be to do with things called magnetic reconnections, which again, magnetic field lines are wiggling around in this corona. Sometimes they break and sometimes they recombine, and huge amounts of energy are transferred from different parts of the sun out into the corona.
I'm beginning to get a sense for how complex
Yeah.
this is. This is not simple.
No, it's really not, but it's really, really interesting.
Yeah.
And it's interesting that we don't have the answer to
Yeah. Okay. So there's the photosphere, there's the corona, which is very, very hot.
And then you have the heliosphere.
The heliosphere.
Now, this is huge. This is kind of the sun's influence in the galaxy, if that makes sense.
Okay. So we're extending out, the photosphere is the sort of last surfacey bit. Mm-hmm. There's the corona, which you said extends out millions of kilometers, right? Which is quite a long way.
Yep.
But now you're talking about the sun's influence on the galaxy, which is a very long way indeed.
Yeah.
So tell me about the heliosphere.
You can imagine the heliosphere as kind of the sun's bubble in the interstellar medium, or the space between stars. So it's where we have a solar wind, which is this flux of charged particles that come from the sun. They create our own little bubble of stuff. Space is not quite as empty as we sometimes make it out to be. And that's the shape of this bubble is really cool, right? This is because the sun is moving in the galaxy, and it's a bit like if you were a bath bomb and you were in your bath. So you've got something which is kind of fizzing out. Mm-hmm. Maybe it's colourful. But if you pushed your bath bomb so it moved from one end of the bath to the other, you would get a shock wave, which is in front of the bath bomb. So it would be sort of blue or whatever the colour is. I'm imagining blue.
This is a fantastic analogy. I'm loving it. Someone's got to try this out.
So
you've
got your
photos.
Blue fizzy bath bomb. That's so it's pushing into the water as it moves towards from one end of the bath to the other. But it's also got this long tail of streamy stuff behind it. And that is the shape of our heliosphere.
We've totally got to try this out. Okay, I'm going to go and get myself a bath bomb. Okay, so the heliosphere is sort of the bath bombicality of the sun as it pushes its way through the galactic medium, the interstellar medium.
Yeah.
Okay, because it's moving with respect to the rest of the stuff in the galaxy. It's pushing through it. Okay. How big does the heliosphere
yeah,
extend?
so it's not spherical because it's got this long
So
tail.
it's poorly named. Well done.
So the part that's closest to the sun, if you like, the part that's going forwards, which is the part that incidentally Voyager 1 and Voyager 2 have left.
Right. Yeah, in one of the many times that we've said that the Voyager spacecraft have left the solar system, it's this one.
So they've left going frontwards, if that makes sense.
Okay, yeah.
So then that's about 150 astronomical units.
150 times the distance from the sun to the Earth. And how remind me again, how far out is...
Oh, so Pluto, you're looking about 30.
Okay, so a lot
60,
bigger than that, yeah.
Yeah, so it is very big, and the tail's much, much longer than that.
So when you're talking about in the analogy with the bath bomb and its fizziness, you're talking about the solar wind, all the stuff which is coming out from the sun, sort of spreading off through the solar system and then out further. And you said that it's kind of like we're living in the atmosphere of the sun. There's this extended, quite thin but definitely there solar wind that extends right out, and that's the heliosphere.
Yeah.
Okay.
Yeah. So that's kind of the basic sort of extra sun structure that we're going to be investigating with all the missions that we're going to look at today.
Okay. Sounds good.
Let's start with the ones that are closest to home. So, I mean, the great place to start looking at the sun is to point some telescopes at it.
Yeah.
Right?
Now, inherently, there's a problem with that, isn't there?
Yeah.
Because if you were to take your standard telescope and just point it at the sun, and bearing in mind the caveat that we did put up front, which is just don't, then there would be a serious issue with that, which is that the sun's quite bright.
It's very, very bright.
Yeah. So what would happen?
You'd just melt everything.
Right.
I mean, it's kind of the old looking, what do you call them? Magnifying glass.
Yeah.
Burning things.
Which you wouldn't do, right? Because that would be very, very silly, particularly not living things. That would be horrible. But that is the stereotype. And you can focus the energy of the sun down, the light from the sun, down to a very fine point and make things burn if that was your desire. So you don't want to do that on the inside of a very expensive piece of optical equipment.
No, but what you do really want to do is have a very, very large aperture. So have a lot of distance, if you like, between one side of the aperture to the other.
Okay, and the aperture being sort of the, if you like, the diameter of your telescope to let lots of light in.
Yeah.
So hang on, why do you want, surely these are working against each other, you don't want to have too much coming because it'll get really, really hot, but you want as much as possible.
You want the diameter to be as large as possible because you want the resolution.
Okay, so the more you can let in, the more detail you can pick out. So big aperture, big wide aperture means higher resolution.
Yeah.
Great. Fantastic.
So it's kind of the distance between the photon that hits the left-hand side of your mirror and the distance to the photon that hits the right-hand side of your mirror. That gives you resolution.
Okay, great. But that's acting in direct counterpoint to, yes, but you're going to burn the back of your eyeball or your expensive camera equipment or whatever it might be to hell. So,
and this is why we don't point the biggest telescopes in the world at the sun.
Exactly, because that would be stupid. Yet, as we said earlier, these amazing images. And look, if you're listening to this on a podcast, we've got the pictures as we go along on these podcasts. If you haven't figured that one out yet, have a look at your phone or your computer right now. There may be an image pointing at you, but also all of the details in the show notes. These amazing, amazing images of the surface layer of the sun with this extraordinary detail. So how?
So, indeed, we have managed to solve the problems of overheating your telescope. So this telescope is called the Daniel K. Inouye Solar Telescope.
Mm-hmm.
It's named after a former U.S. senator of Hawaii. And the telescope is located on the island of Maui in Hawaii.
Right. There's a bunch of them there, aren't there? Because it's a really good place to have them because it's right up on top of mountains and there's not a lot around and really clear skies.
Yeah. It's about 3,000 meters up. So
awesome.
It's very, very good.
Okay. So big telescope in Hawaii.
Yep. And so it's about 4 meters in diameter, this telescope.
Okay. So that's quite big.
It's quite big. It's quite small in terms of what you might think of for a nighttime kind of observing telescope for the stars and galaxies.
Sure. I mean, there are much bigger telescopes.
Yeah.
But they're not being pointed at our closest star, are they?
Exactly. You've got a whole lot different set of technical challenges if you want to do this kind of work on the sun. So it is the largest solar telescope. And we got these beautiful images through because it just came online and produced its first kind of test images in
So
January.
this is sort of, I mean, maybe not quite first light, but these are the test images, and it's already making front page headlines. That's not bad.
It's
That's
absolutely beautiful. So the videos that you see are of the turbulent plasma that's on the surface of the sun, and they're things called convective cells. Now, these videos and these images are the highest resolution we've ever been able to have of the sun. So,
It's amazing. I mean, there's all of these. It's almost like tiling, except that it's moving tiling. Like it's clearly there's a lot going on the surface of the sun, but so much detail. These little, what did you call them? Convective cells. So what are they? What are we seeing?
So
there?
they're giant bubbles, basically.
Okay.
It's very similar physics, and to if you put your pot of water on the stove, you get bubbles which form in the bottom, and then you get convective motion which pushes them to the top, where they kind of, sometimes they burst if they're full of air, but then if you think about the cool edges sinking back down into the sun, they form the dark rings, and then you get the bright hot material in the center.
So the sun is just covered in this mosaic of these hot bits coming up, cooler bits sinking back down. It's amazing.
Yeah,
It's gorgeous to look at.
Each of those bubbles is about the size of Texas.
Wow. And yet, when you consider how big the sun is, which is, what, millions of times bigger than the Earth?
Yeah,
Is
you
that
could
right?
fit 1 million Earths inside, yeah.
Then that's a lot of bubbles.
It's a lot.
It's
yeah.
a lot of bubbles.
So the resolution on this image particularly is something like the smallest detail you can see is about 30 kilometers in size.
Wow. Sorry, I'm just sitting back for a second. That's amazing.
Yeah.
Absolutely amazing. Okay. How do you point a 4-meter telescope at the sun without everything catching on fire?
Okay, so first of all, they've got this really interesting donut.
Okay.
And I didn't actually plan this when I said
But there
offered
we
you a
are.
donut
Yeah.
this morning.
We should have seen that coming a long way away.
But it's this heat stop, and they call it a cooled metal donut, and that blocks quite a lot of the sun's energy from actually entering the telescope.
So it's literally just a barrier. It's a shade put over the front to block out most of it, but let a bit through.
Yeah, and it
Okay.
just happens to be donut shaped.
Yeah, okay.
It's really rather nice. Another thing is that you've got to cool everything that basically the light sort of goes through and touches. And to do this, it's a little bit unlike ground heating. What do you call it? Underground heating?
Underfloor heating?
Where you stick pipes in the ground. And you
Oh,
just
I
kind
see.
of
Right. Yeah, geothermal
Yeah,
heating. Right.
except on the opposite.
Right.
Because up on the top of a mountain, it turns out the ground is really
Quite cold. Yeah.
Yeah. Which is very useful because,
Yeah.
there's a lot, it's often snow and ice on the ground.
If only we had a way to cool this really, really hot thing, they said, on the top of a mountain in Hawaii.
Yeah. So they just sort of shove the heat down these tubes and it cools down.
Cool.
It's really quite clever.
Yeah.
But it's something like 11 kilometers of pipes that you can pump the heat down to cool it down.
So they're getting rid of a lot of heat then. This is not mucking around.
Yeah, so dumping all this heat. So it's very, very cool. And it's this is totally revolutionary for ground-based solar observations. I think the previous largest solar telescope was something like 1 meter.
Mm-hmm.
We're moving up to 4 meters.
Which is considerably more.
Yeah. And once everything's sort of up and running, they're expecting to go down to even smaller
Finer resolution.
Yeah.
Yes.
I'm trying to mix two
Smaller
ideas there.
details. Yeah.
Yeah. So something like 20 kilometers is the target.
That's pretty good.
Yeah. And you've got these wonderful brand new adaptive optics systems.
I was going to ask, because they're looking up through the atmosphere. So this is earth-based, ground-based, even if it is on top of a mountain. You're looking through a very wobbly atmosphere at details on the surface of the sun, which are tens of kilometers. It's not easy.
It's really
not
not
an easy
It's
thing
really
to do.
not. In fact, the atmosphere has been astronomers' bane forever, basically.
Yeah. So because I remember quite some time ago we did an episode of the podcast which dealt with the two different kinds of modern optics trickery that you can have on telescopes. One of which was adaptive optics and the other one was active optics. And you said this is adaptive. So remind us of the difference between the two.
So adaptive means that you're changing your observations to suit the conditions. So you're adapting is where the word obviously comes from.
Sure, but how?
So this,
How are you doing
this
that?
can be doing things like deforming the mirror to back correct the waves that are coming in.
Is this the one where you shine a laser up into the atmosphere to measure what's going on?
So you can do active and adaptive optics with your
okay.
lasers.
Right.
It depends on how you actually do the correction. So the two ways you can either correct the light as it's coming in by deforming your mirror or doing something similar, or you can take your image later on and back process it. So either one gives you a much, much clearer,
Sure.
higher resolution picture.
But either way, you're considering what's going on in the atmosphere and how that wobbliness is going to affect your image and then correcting for it either live or in post-processing
Yes.
to make these amazing images.
Yeah,
Cool.
and these are some of the most advanced systems in the world to do this, because astronomers have been working on this for a really long time.
That's awesome. So this telescope,
Yeah.
once it's managed to get through its test phase, which it seems to be doing reasonably well, what's it wanting to find out? What's its main objectives?
So we really want to map the magnetic fields that are going on in the corona, because as we said, this corona is really, really hot. We don't necessarily understand the reason for that, so we want to get some more data that might help give us some more clues. We want to know how particularly the magnetic fields are created and destroyed or reorganized within that corona to tell us something about that. And also, very, very importantly, we want to know how the variability of the corona happens and how that might be linked to broader space weather. Because we live, as we say, we live in the atmosphere of the sun, which means the weather from the sun matters.
Yeah.
It really matters. If you have solar storms, if you have coronal mass ejections, these are the enormous explosions off the surface of the sun.
And some of those are huge.
Yeah, they send charged particles towards us, really damaging radiation. They're a risk to human life, especially human life that's in space. So the International Space Station is always at risk. And so we
Not
have
to mention, global communication networks and
Definitely,
all of that.
yeah. So there's been instances of when we've lost really key GPS satellite technology or communication technology. In the past, there's been storms that have just caused us that if they happen today would completely destroy a lot of modern communication.
Yeah, I mean, I remember reading a while ago there was one of the Solar Observatory, the NASA Solar Observatory, anyway, one of those had amazing images of a huge, solar flare coming off the surface, and it was, I don't know, dozens of times the size of the Earth itself. And if it had been pointing in our direction, just would have wiped out all of the satellite communication and probably quite a bit of the land-based stuff as well. Would have given us some really, really good northern and southern lights. The aurora would have been great, but we wouldn't have been able to text anyone to tell them about it. But it just wasn't pointing in our direction. And I guess that's always kind of a risk.
Yeah,
Want to keep an eye out for?
There is always a risk from the sun. So the good thing about that is that when these things do happen, we get advance notice. So things like we can pull astronauts down from and put them back in the atmosphere, which is a bit safer, things like that. But we need to develop better predictive models, better warning systems as well. So that's part of the mission as well.
I do find it really interesting that this telescope, everything you've just described is, about the corona and studying space weather and so on. The distance between what the research is actually interested in and how that's carried out, and the visuals, what makes the front page of the newspaper and is all over all the news. These amazing images of these beautiful convective cells on the surface of the sun. And sure, okay, I'm quite prepared to believe there's a very strong connection maybe between those and what the telescope's actually setting out to study. But actually, no, we need some really good visuals in order to be able to sell this program. It's marketing in a way that it's. I wonder how many people really realize how different astronomical research is from astronomical imagery. Anyway, I'm just going to leave that there. It's an interesting thing.
Yeah, I will just point out that though, when you look at the science goals for a particular telescope or a particular mission, they are big, broad summaries, right? If you took each of those very few things that I mentioned, there's probably a dozen, maybe 20 or 30 independent little projects that might be contributing to that. In each of those projects, you might be talking about a few dozens of researchers who are looking at different aspects of those projects. So, and even those might only tenuously be linking up to that goal. They might be doing something slightly different. And then as you get the technology and get used to it, you think of more creative ways to exploit it as well. So they are big, broad umbrella statements. And the study of the photosphere is an important part of what this telescope is. I don't want to belittle that side of what they're doing.
No, and I'm not either. It's always fascinated me, and it's one of the reasons why I really enjoy doing this podcast. It's always fascinated me that astronomy, astrophysics is so beautifully visual. And yet, often the visible, like the visual sides, the images and the videos are not the research. That's not what it's about.
Yeah.
It's just a really nice byproduct of looking at stuff in space.
You're going to see those transformed into amazing graphs when you read the scientific articles.
I'm sure.
Yeah.
Okay. All right. So anything else to talk about with this massive, but no, moderate-sized 4-meter mirror on the top of a Hawaiian mountain?
So this is our telescope's going to be up and doing its science operations from the middle of this year, from I guess it would be our summer, but from July.
Okay.
So it's going to be in full science mode from then. I would expect to see a lot more amazing imagery very soon.
Looking forward to that one. Okay, so that's the first in our trio of pretty amazing research instruments. The other two are not on the ground. They're in space.
Yeah. And one of them's only just very recently got to space.
It's just launched, a couple of weeks ago?
Yeah, so 10th of February was the launch of the Solar Orbiter.
Mm-hmm.
So this is a mission that's being led by ESA, so the European Space Agency. And what they want to do with this particular Solar Orbiter is to look at mapping the poles of the sun.
Right. Now, I've only really just thought of this. I'm assuming that we go around the sun in pretty much roughly the same plane that the sun is itself spinning.
Yep,
and
that's
so
true.
when you're talking about the poles of the sun, have we ever seen them before?
That's a good question. I don't know. I don't think we've certainly never studied them in the kind of detail that this orbiter is going to.
Because I would have thought that we'd have to go a very, very long way out of our way to be able to see them.
Yeah.
Because you've really got to go right up out of the plane that the entire solar system is in order to actually get a good view of them.
Yeah. So the thing to remember with the sun is that it's hard to get to generally, actually.
Yeah.
And it's quite hard to get things into these orbits that are perpendicular to the plane of the orbits of the planets.
Now, why is that? Because you were mentioning that before, and it's actually really interesting because you do kind of think, oh, it's it's the sun, it's there. You just we're all in orbit around it. You just go there.
Yeah.
You just leave the Earth and we'll just fall down towards the sun. Not that simple.
It sounds really easy.
It does.
It does. So if you think, well, let's give a mission to Mars.
Okay.
We're often told, well, a mission to Mars will take something around 8 months when Mars is relatively close to the Earth. And that's about half the distance that the Earth is to the sun. So you'd think, well, it might take about a year to get there. The solar orbiter is going to take 3.5 years.
3.5
to
years.
get to its orbit.
That sounds far more difficult than it ought to be. So what's the issue?
Well, it's not easy to go inwards in solar systems and orbits.
And why is that?
So, because let's imagine the Earth has got going around the sun and it's got a particular speed.
Yeah. And as we've mentioned before, the orbits are defined by their distance out from the sun, from the thing that you're orbiting around, and they have a very specific speed. You can't be in orbit at a particular place without going at a particular speed. That's how that works.
Yeah. And so the Earth's going around at something like 30 kilometers every second.
Okay. So we're going 30k a second, and that's our orbital speed. And
Yep.
everything on Earth is going at, call it 30 kilometers a second, slightly different depending on which side of the Earth you're on. But yes, 30k a second.
And if you want to go to an orbit that's slightly further out from the sun, you've got to speed up a little bit.
Yeah, you've got to be going faster.
Now, that's actually a pretty easy thing to do because if you launch your satellite or your mission, then it's already going at 30 kilometers a second when it leaves the Earth, and then you're just kind of boost it a little bit.
Yeah, burn a bit of fuel, speed up.
Bang, you're done.
Yeah,
Easy.
easy.
And you can get to Mars. If you want to go inwards, you've got to slow down.
Yeah.
And it's the slowing down that's hard because you have to shed a lot of speed to get close to the sun.
Yeah. If you wanted to slow down a little bit, I guess you could turn the motors around and push yourself back against your 30k a second. But getting down towards the sun, you've really got to slow down a lot.
A lot, yeah. So it's a huge slowdown that you've got to do. And what's worse is that you don't have anything, well, you've only got one thing really to help you to get there.
Venus.
Which is Venus, yeah. So when we go to the outer solar system, especially if you want to go really far out in the solar system, you might have heard of these gravity assists that we use.
Yeah, around the big planets, Jupiter and Saturn.
So we just can't burn fuel. Let's say we're going to Pluto. We can't just burn fuel until we get to Pluto. We couldn't possibly carry enough fuel, and then you get too heavy, and then it just goes awfully wrong.
Yeah, but you can borrow a bit of energy, a bit of momentum from the big planets and swing by them, which is why all of those sort of far-flung missions have always done multiple stops by Jupiter and Saturn on the way out. It's not just, hey, well, we may as well. It's, no, we kind of have to because we can only get that far before we need a boost.
Yep.
And you swing on around and you grab some energy from the big planets, and that helps you to boost out even further. You can't do that going down towards the sun.
Yeah, no, there's just no Jupiters and Saturns between us and the sun.
Yeah. Okay, so that is hard.
Yeah, so the only thing was significant, I mean, there's Mercury, but it's kind of little. So we tend to use Venus because it's much, much larger.
Sure. So you can do it, but it's still a very difficult thing.
Yeah, so for example, I think there's going to be about 7 different gravity assists that the Solar Orbiter mission is going to do with Venus. Yeah.
Wow.
Yeah, so it takes time.
Yeah.
You've got to do it several times to slow down enough to get...
And that's a lot of maths.
Yeah.
It's a lot easy to do. So what is it going to... I'd love to see the orbit of this thing. I must look that up. So is it going to sort of, loop around it a few times or sort of swing on past and catch it the next time it comes around on orbit? Or how?
Yeah, so it is doing the latter thing. So it's catching Venus every time it sort of goes around in a loop. Now, what we need to... I guess not think about is that the solar orbit is not actually going to be in a circular orbit around the sun.
Okay.
It's going to be in this very long elliptical orbit where it actually comes out nearly back to the Earth's orbit. So something like 0.9 of an astronomical unit, the distance between Earth and sun. And then it goes into about something like 0.28 is the closest.
Right. How close is Mercury?
So, that's about 0.3 as well, I think. So it's very similar.
So it's going just inside the orbit of Mercury, which is pretty close.
Yeah.
Pretty close.
In terms of kilometre distances, it's something like 41 million kilometres is the closest approach to the sun, which sounds like a lot. Mm-hmm. But remember, the sun's big.
Yeah, that's right. So you don't want to get too close.
It's about 60 times the radius of the sun.
So, I mean, if you put it that way, that's pretty close.
Yeah.
Okay. So it's on this very elongated orbit where it's getting in quite close, but then swinging out quite a long way away. Kind of like a really close-in comet. In a sense, comets get in really close and then fling themselves right out to the outer reaches. Yeah. This is sort of coming out, say hi to Earth, and then I'm going to go whipping back in towards the sun again. Okay.
And then when it's close, it can do some really interesting measurements of inside the corona. And then when it comes back out, it's a nice time to, cool down, first of all, but also to communicate with Earth.
Sure. But you also said that its mission is to have a look at the poles. Mm-hmm. So this orbit is not in the same plane as our orbit? It's kind of going
it's
perpendicular.
pretty much perpendicular.
Wow.
Yeah.
That's cool.
So we'll put some diagrams in the show notes.
Yeah. So it's, with any luck, going to be throwing us back some data and some pictures of, aspects of the sun we've never seen before.
Yeah, I mean, the reason why we want to look at the poles is all, again, to do with this magnetic fields of the sun. So the magnetic dynamo of the sun, the magnetic field generation, comes from the global magnetic fields from the whole plasma. And it does have an we think of the magnetic fields as being sort of fairly straightforward things because the example of, say, the Earth's magnetic field is pretty straightforward.
Fairly simple. It's very much like, in not really, but kinda, a big bar magnet down in the middle of the Earth, with a north and a south, and the magnetic field lines stick out the top and loop around and come back in the bottom, or the other way around. Can't remember which way they go. And that's pretty simple, but the sun's not.
No, the sun's not
simple.
So simple.
Doesn't have a simple pole, a bar magnet down in its core?
No. It's got a north and a south pole.
Yeah.
And there are some sort of global magnetic streams that work with those. But because you've got this roiling plasma on the surface, that again, charged particles, then all of the magnetic fields sort of start to twist and bend and buckle and break.
Magnetism's weird. I mean, the more you study about magnetism, and it's, magnetism comes from like bar magnets. What even is that? It's basically a lump of rock that's got this magical power of magnetism. But when you study it, magnetism comes from moving electric charges, electric stuff moving around. And so if you've got plasma, which is effectively a gas of charged particles, then that's a lot of charged stuff moving around in really complicated ways, which is going to give you really complicated magnetic fields, which is going to be challenging both visually and mathematically to figure out. That's cool.
The sun has a cycle of this. So the sun has an overall 22-year sort of cycle that it goes through. What we really observe is an 11-year cycle. And what that means is that the sun starts off as kind of fairly calm, the magnetic fields are mostly kind of doing calm, useful, well, not useful, but, sort of...
Simple, calm.
Yeah, it's sort of a little bit bar magnety on the surface. But then what happens is things start to change, and the sun has differential rotation of the plasma, which starts to drag magnetic fields around with the charged particles, and this gets more and more chaotic as time goes on. And eventually the whole surface of the sun gets... so we get all this magnetic activity, we get sunspots, we get flares, everything just kind of gets to a really high peak. And then at this point, the sun's magnetic poles switch.
Ooh, that's exciting.
They just flip. So the North Pole becomes South Pole, the South Pole becomes the North Pole.
Wow. And this is over an 11-year cycle.
Yeah, and you kind of reset that whole process again.
And start again.
Yeah. And so therefore it's 22 years to get from north to south to south to north again.
The full cycle is 22 years.
But what we see in terms of activity is kind of a peak every 11 years.
Right. Where are we at in that cycle at the moment?
So we're just coming out of a minimum.
Ah.
So, I mean, it's a good...
So the coming decade could be quite fun then.
It's a good time to launch a solar probe because we might be getting a whole lot of more activity over the
Maybe
next
not
few
a great
years.
time to be in the satellite communications business, though.
Well, yeah, it's interesting because the sun's been behaving quite strangely over the past couple of decades. It's been more in the minimum than it has been in the past. I mean, we've got observations that go back a couple of hundred years with sunspots and things like that. And in the past, the solar cycle's been much, much more regular than it is currently. That doesn't mean it's not doing its thing. It definitely is. It's just taking a bit longer than we thought to come out of minimum.
Go figure, the sun's complicated.
And not always, reaching the maximums that we were expecting. So
okay. Bottom line is magnetic fields on the sun are interesting and complicated. And if we swing around the poles, we'll get a really good look at that, particularly at a time when a lot of stuff's going to be happening with the sun as it gets around to switching. Ooh.
Yeah. So, over the next sort of 5 or 6 years is a key point in time to be looking at the sun.
Awesome. Okay.
So that's a really exciting mission. And it's one of these missions where you do have to design a whole lot of new technology into your space probe as well.
Mm-hmm.
So you can imagine if you're going to get that close to the sun, you might not want to be too hot.
No, one would think that would be an important design parameter for this particular thing.
Yeah. So the solar orbiter, for example, has got this big heat shield that will protect it for temperatures that are more than 500 degrees on the space probe.
Yeah, that's hot.
Now, that's maybe not that impressive if we compare that to our other solar orbiter that was launched just over a year ago, and that's the Parker Solar Probe. Now, the Parker Solar Probe's been designed to go much, much closer into the sun. So it's got heat shields that need to protect it from temperatures more than 1,300 degrees.
Oh, that can't be easy to design for. Okay, so hang on, back up a minute. The Parker one launched a bit over a year ago.
Yeah, 2018.
2018. Yep. And it's going in closer. So it's not going to be going around looking at the poles. It's going in even closer. How close?
So the closest approach that it's done so far was actually last month as well, in January 2020. It went to 19 million kilometres off the surface.
Okay, so remind me, how close was the other one going to go?
41.
41. Okay, so that's like around half.
Yeah.
Or,
so we're talking
twice
about
as close.
30 times the radius of the sun.
Wow.
So that's the closest, and that's why it's currently the closest artificial object to the sun.
Yeah.
And it's going to remain so for quite a while.
And so does it remain on an orbit which stays quite close to the sun, or does it swing out near us as well?
No, it's got an elliptical orbit. It doesn't quite swing out as far as us. But what it's doing in these orbital loops is every time it's getting a little bit closer.
Ooh, does that mean it's going to keep doing that and eventually just burst into flame?
It's going to get really, really close. So in 2025, it's going to be... about going at crazy speeds, first of all. It's going to become the fastest man-made object ever.
Wow.
It's going to be going something like 200 kilometres every second.
That's just nuts. That's crazy.
That's amazing, which is, I converted it, it's about 700,000 kilometres per hour.
Wow.
Absolutely crazy. And it's going to go as close as 10 solar radii. So
serious?
7 million kilometres.
So that's like 1/3 the distance out to Mercury.
Yeah.
Holy cow.
That's why
nuts.
it needs to have some really good heat shields on it to get this close.
That's really crazy. I think I was reading the other day, though, that, and I can't remember whether it was this one or whether, what was the second one that we talked about?
Solar orbiter.
The solar orbiter. Can't remember whether this was about the solar orbiter or about the Parker probe. But you've got the side facing the sun, which is really, 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 really hot. And you've got the side facing away from the sun, which gets really cold to the point where they actually have to heat the instruments on the other side in order to keep them operating, which is bonkers, but that's kind of how space works.
Yeah, and it's amazing the technology you have to put into these things because, I mean, the sun's 8 light minutes away, right? Which means that takes 8 minutes to communicate with anything that's close to the sun.
Yeah, that's true. It goes the other way.
So if you had your heat shield up and your instruments were all lovely and protected, but if you went a little bit off balance and you wobbled a bit and you turned a little bit so that that heat shield wasn't protecting your instruments, it would be too late for the space probe to send a
It'll be cooking
signal.
for 8 minutes before you go, oh,
Or
quick
16.
turn. Well, 16, that's right, because it's got to come and go.
Yeah.
16 minutes of frying at that distance from the sun.
Yeah, you just melt
It's gone.
everything. Yeah.
It's gone, isn't it?
So these probes are designed to be autonomous
Mm-hmm.
and that if they detect that something's gone wrong and they're heating up a bit too much on the sides, they will correct themselves.
Goodness me. That's absolutely nuts. So, what is Parker wanting to do?
Yeah, so Parker's it's doing these dives. They call them dives. They're actually going very, very close to the sun. And there's a few reasons why you want to do that. You want to learn about, again, parts of the corona. So we're going deeper into the corona than we ever had before. We want to learn about the energy that's particularly leaving the corona. So we want to know about that connection of energy between the sun itself and the corona, and how that, again, transforms out to the second step, if you like, out, which is the solar wind. We want to learn, again, magnetic fields, super important. What are they all doing? And the particle streams as well that are coming across these super energetic particles.
Wow. And how long you said that the dives are sort of getting a bit closer each time. Is there a final dive planned? Is that
No, not yet. So as with every mission, so the mission lifetime is about 7 years planned so far for the Parker Solar Probe. Everyone's hoping for extended missions, right?
Okay.
So
okay.
extended
So
missions
it's not sort of built in as like, okay, this is the last one. We're going to go really close on this one and see what we get.
Not at this stage. I think we want to see if we can push it a bit longer before we pull that final switch, I think.
Okay, so just to recap then, we've got our ground-based 4-meter telescope sitting on top of a mountain in Hawaii, which staggeringly can take these amazing pictures without bursting into flame. We've got the brand new probe, which is about to, it's got like a year-long mission to
7
get in.
years.
7, sorry. I mean, but year to get into its orbit.
3.5 years till it
3.5
gets there,
years.
yeah.
Come on, Chris,
You
keep
got to
up.
wait. You got to wait.
That's a long time, but it's just launched. And then we've got Parker, which is in there doing its thing already, getting really close to the sun. This is a brave new era for solar research.
Yeah, I mean,
This is cool.
I would say it would be a great time to become a solar physicist. right?
Yeah. If you're casting about for, I don't know what kind of physics I should study, this would be a good one.
Yeah.
Yeah.
And there's a lovely thing. So NASA is who's running the the Parker probe, and ESA is kind of mostly in charge of the solar orbiter. This is all part of a sort of a bigger network of observations that we want to learn about the sun and learn about our place within our solar system in relation to the sun. And the whole project this is my favorite bit. It's called Living with a Star.
Living with a star. That's nice.
It kind of sounds like you're living with a disease.
Or, I don't know, you sort of, got this new friend in a cupboard, do you want to come and meet my star?
I like it, but it also sounds a little bit like living with tuberculosis. And I'm not really sure if you're saying that the star
Are
is...
you feeling all right today, Emily? Yeah, I've just got star. Okay.
Putting up with the star.
You can get a shot for that. Ah, dear me. Well, that brings us to the end of this very suntastic episode of...
Was that your joke?
No, it wasn't. It was this. Living with this, it sounds a bit like a disease. That could be coronavirus.
Oh, no.
Too soon?
Oh,
Too soon.
no.
Okay, sorry. Apologies to everyone out there who actually might be dealing with coronavirus. Sorry about that. Listen, if you want to get in touch with us on the show, whether it's to complain about our sense of humour or to suggest topics for a future episode, you can do that in all sorts of ways. Emily, how?
You can definitely tweet us your best sun jokes.
You can. How do they do that?
At SyzygyPod, so
Yes.
SYZYGY pod.
Indeed. Are we on any other social media, Emily?
Oh, yeah, we are.
Yeah, we are.
We're on Instagram.
We are.
On Facebook.
We are. We're not on TikTok. We've discussed that.
We're not on OkCupid. Is that even a thing anymore?
No, we're definitely not on any of the dating apps. But we do have a website, syzygy.fm, where you can find all of the past episodes, all of the show notes. Just a little reminder, we put in quite a lot of effort every week to cover our podcast in links and photos and stuff. And if you're missing out on that, you're missing out on that. There's a lot of really good stuff in there. Astronomy is a visual thing as well as an audio thing, turns out. If you want to help the show, then tell people about us. Go and spread the word. Find a person in your life who you think might enjoy it and tell them about it and get them to go and have a listen. That's by far the best way. The other way is that you can help us keep the electrons pumping through our website and through the podcast medium itself by going to patreon.com/syzygypod and throwing a few dollars a month our way. It genuinely does help us to keep it all going. Otherwise, we've got, I guess, one last thing to talk about, which is in a few months' time, still early days yet, but in May, in the middle of May 16th, we are going to the grand city of Hull for the world's first Northern Podcast Festival. It's going to be great fun. We're going to do a live show there, Emily. Any ideas what we're going to talk about yet? Space. Probably a good idea. So if you're in the Hull region or you feel like just visiting the great region of Hull, then go to northernpodcastfestival.com and have a look for us there. You can get the tickets already for the very, very cheap price of £2.67. I still can't say that with a straight face. That's just so silly. Come along and see us. We'd love to see you there. Otherwise, we will catch you again in roughly a week or so for some more astronomical goodness. Catch you later, Emily.
See you later.
Bye, everybody.
The other way you could think about living with a star,
Yeah.
I was just thinking, it's almost a bit like living with raccoons.
Oh, sorry, explain that. Yeah.
Well, it's like, you've got this kind of thing that you have to live with and maybe sort of clear out of the attic from time to time.
Why is there garbage all over the lawn? Oh, it's that bloody star again.
Or a teenager.
Yeah, I can write a self-help book. How to deal with
They're
your
fairly
star.
explosive, I'm told.
They can be. Definitely can be.